Hello, everyone. If you've used a computer, you have used a machine that is broken and experienced brokenness of some kind, I'm sure. And this usually manifests itself in one of two ways. Either it just doesn't work, so this would be maybe an error page like this one, or it does work, but it's really, really slow. And from a user's point of view, both of these are really bad, right? It basically makes a product unusable. OK, sorry, not sorry, but let's talk about error pages for a minute. If you're going to show the user an error, at least put something cute on there, like a cat. So instead of showing an error page, show them this, or maybe even this. See? You're not even mad anymore. You're feline a lot better. OK. I'm going to get serious again. Computers. These things. At least that's what we usually think of when we hear the word computer. But in reality, most programs these days run on this kind of computer. Almost any non-trivial application doesn't run on a single machine. It runs on a set of connected machines, and we call this a system. A production system is a system that serves real users. And in order to keep the system running, someone needs to operate it. So we call this operations, or ops. And basically, it's all the stuff that you do once your code is running in production. Why should we care about this? Because we're making things for people to use, and we want them to use it and experience joy and happiness. Kind of like the joy and happiness that I experience every time I look at the logo for this conference. It's just so amazing. It's one of the best things I've ever seen. And it just makes me feel warm and fuzzy inside. Speaking of things that make me feel warm and fuzzy, let's talk about failure. Why do systems fail? Why does this happen? In order to understand that, we need to understand what a production system really is. So if you are someone who writes code, your code is the thing that you will be interfacing with the most. That is your world, so to speak. And this is your product, could be a website, like, I don't know, video hosting or something like that. But then there's all this other stuff underneath it. So the application really runs on this stack of software and hardware, where we have the operating system, we have the actual physical machine that has components like a CPU and memory, and that's connected to this network, which then connects to the further internet infrastructure, which is mostly these cables at the bottom of the ocean. And all this stuff, we just call it the cloud, and basically pretend that it isn't there. But just because we pretend it's not there doesn't mean it's not actually still there, right? And each component in the stack is something that can potentially fail. And given enough time, it will fail. So this is a very blurry image of a shark biting into a submarine internet cable. It's a wire shark. I find this quite shocking. It's a pretty large bite. One might even say a megabyte. And there's a lot more where that came from. So we have cosmic rays coming down from space and randomly flipping bits in memory. We have disk failures, which actually do happen quite a lot, power outages, software and hardware bugs, and the list keeps going. And all of these fall into a category of failure that I like to call entropy, which mostly consists of random events. This stuff is impossible to predict. It just kind of happens, and it can happen at any layer in the stack. And to some extent, we kind of just need to accept that this kind of thing is going to happen. It's outside of our control. This is the physical reality that we live in. There's a second category that has to do with resources. So every component in a system has a certain limit to how much load it can handle. And this is called the capacity. The capacity is a measure of how full a system is. And there's always a limit to how much it can handle. When the capacity is exceeded, work will either get queued or rejected. And this usually happens when you get more traffic than you were prepared for. You've probably experienced this in a full restaurant where the wait staff is overwhelmed and you're waiting forever to get served. What's kind of difficult about capacity and understanding capacity is that it's not linear. So everything is kind of fine until you hit that limit, and then everything is just completely terrible, which is illustrated by this hockey stick curve where the queue time or wait time just kind of goes to infinity. So what happens when failure actually strikes? Well, failures are often not isolated, and especially if failure is kind of rare, then the error handling is not something that is very well tested. And so that means that if one component fails, it's quite likely that it's going to take a bunch of other components with it as well. And sometimes this can even cause feedback loops where errors just go round and round in circles, which I like to call particle accelerators. So this kind of failure is sometimes also called a cascading failure. And in general, it happens because in a distributed system, all of these parts are connected and depend on each other. So there's a lot of potential for failure. What can we do about it? Can we prevent an isolated failure from affecting the rest of the system? And the answer is yes. So the way that the main way in which we can address this is through redundant redundancy, which basically means running several copies of your application on different machines. So if a shark comes along and bites into one of them, then the other one is still able to serve the traffic. And this is often called high availability. It's a really effective way of protecting against entropy-induced failures in particular. And if you think about it, this is something that we find in nature as well. The human body has a lot of redundancy built into it. For example, most humans have 2 kidneys. If one of them fails, the other one is still able to take over, right? So your kidneys are highly available. Interestingly, this very same mechanism can also be used to help address capacity issues. And this is referred to as scaling the application. And I bet you've seen this one in the supermarket. So the queues are piling up, and someone's called in to open another cash register. That's an example of adding capacity to serve a rising demand. And in a computer system, this works pretty much the same way. So handling traffic in general requires resources, mostly CPU and memory, depending on what your workload is. And in order to be able to handle more traffic, you can add more machines. And this is generally referred to as horizontal scaling or scaling out. So once you have a lot of different computers, you need a way of actually distributing the work between them. And the way that you do this quite often is a queue. So you have a lot of consumers that are able to consume work from the same queue and balance the work between them. And this works pretty well for stateless applications where you don't really have to store any data, but you need to store the data somewhere. And in most system designs, there's usually an elephant in the room, the database. Databases are notoriously difficult to scale. And in general, it's just difficult to get different computers to agree on what the current state of the world is. Kind of the same with humans, actually. And for this reason, databases will often become a single point of failure and a scaling bottleneck, because chances are you only have one of them, right? But there are techniques such as replication and sharding, and those allow you to get horizontal scalability at the database level as well. Those generally are not that easy to manage, but it does allow you to eliminate single points of failure. Reliability is not just about the components themselves, though. It's also about how those components are connected, the arrows between the boxes, if you will. And this is especially relevant in the case of cascading failures. There are patterns that can help you deal with this and try and isolate failures. And one example of such a pattern is the circuit breaker, which works pretty similarly to the circuit breaker in your house. So when a component is getting a lot of errors from another component, it can basically just stop sending requests for some period of time to let it recover. And these communication interfaces between components are really leverage points where some rather small changes can have a pretty big impact on reliability. But regardless of how the system is designed, if it's running in production and has users, then you probably want to know what's going on. Like, what is even happening? And that really requires a real-time view of the system, which is what we call monitoring. And monitoring is, in many ways, the foundation of operating a system in production. So with all of these pieces, we have services, message queues, databases. There's a lot of components to monitor. And all of these components are not just sitting there. They're constantly doing work. And there may be hundreds of requests per second running through the system at any given point in time. Watching every single one of those requests, that's not going to work. Like, you can't scroll that quickly. You can't read that quickly. So really, you need to aggregate this information into metrics. And a metric is pretty much just a number over time, which you can then use to plot charts like this one, which really helps spot outliers and changes in behavior over time. But where do we even start? I mean, you've seen the stack of things. There's so many layers, so many things that we could monitor. And yeah, if you try and collect as many metrics as possible, you're probably going to drown in them. There's just too many things. So really, we need to take a step back and think about, what are we actually trying to achieve? And the answer to that usually is a good user experience, which in the context of operations usually means two things. The service is responding, and the responses are fast. That's it. And that is quantifiable. So one way of characterizing the service behavior is by using what is called the golden signals. And basically, these are high-level metrics that can tell you a lot about the current state of the system. So we have error rates and latency, which tell you exactly those two things. Is it working? Is it fast? The error rate you will measure in errors per second. You might want to compare this also to the traffic, which is in requests per second. And if this goes up, you know that something's probably broken. And then we have slowness. So this is often also called latency. And latency is a measure of how long something takes. So we usually measure this in seconds or maybe milliseconds. And you know you have a problem when your users need to wait and see what the response is going to look like when they finally see the page. So for latency numbers, you'll want to understand not just the average behavior, but also the worst case. And this is something that all monitoring, or almost all monitoring products do. They will show you the average, but they won't show you the worst case behavior. And typically, you will have a lot of very fast responses and then a few very slow ones. Those slow ones really, really matter. As an analogy, if you're sitting in a restaurant and you're waiting an hour to get served while everyone around you is getting served very quickly, you're probably not that happy, right? So this is why this matters. Then we have saturation. Saturation is another word of having reached your capacity limit. And a common way of measuring this is queue length or queue time. And basically, once things are getting queued, you probably have a capacity problem. So you can take these metrics and put them on a dashboard, and now you already have a pretty good idea of what is going on, just from these 4 numbers alone. And if you have a lot of different components, you can put one row per component, and now you have a good understanding of what is happening across the entire system. So this tells you not just about the individual components, but it tells you about the relationship between those components. Because you can see which things are correlating. And this really helps understand changes in behavior, changes over time, and it also helps you anticipate capacity needs. Okay. I've talked a lot about the computer stuff, but at the end of the day, computers don't exist in a vacuum, unless we're talking about unmanned spacecraft, which literally do exist in a vacuum. But anyway, we have human users and human operators. And so how do we users fit into all of this? Let's talk about the human element in failure. Here's a true story of a real thing that really happened. So this is a button. And yeah, it doesn't look very red, but it's a red button. Do not press this button. Bad things will happen if you press this button. You pressed the button. Your database is now gone. One could say that you dropped the base. This is a scenario that has happened to a lot of companies over the years, including the one that I work at just a couple of weeks ago. And an easy response in this scenario is to say, bad human, you are to blame. You must be fired. But maybe, just maybe, we should not assume bad intentions and try and find out why the button was pressed in the first place. Because the chances are that there's just something very confusing about the button or something confusing about the process. Also, why does such a button even exist in the first place? Maybe it shouldn't exist. So if we go back to this technology stack, it's really missing some crucial bits because we are humans. We interact with the system, and really, we're part of the system, just a cog in the machine. And in fact, humans are involved at every layer of this stack. It's basically humans all the way down. So when it comes to epic failures like this one, instead of blaming the person who pressed the button, maybe we should think about how the system failed this poor human, because there's almost always systemic factors at play. And this is something that we see in the safety-critical industries like aviation and medicine all the time. The way that we respond to these kinds of events really matters. If you have a blameless culture, that makes it safe to talk about these issues. And that is crucial in order to understand what actually happened. And only when you really understand what happened can you improve the safety of the system. So the next time you nuke your production database, celebrate it, and then get rid of the button. So to recap the main ideas, a production system serves real users, and there's sharks biting into cables. Users of those systems like to use things that are fast and work, and monitoring can help you tell if that is actually the case. And finally, epic failures are almost always because of systemic factors, and improving safety requires systemic changes. That's all I got. Thanks.